Theorems on open sets in metric spaces. The very first one is, in any metric space XD, the empty set phi and the metric set X itself both are open. We need to prove that both are open sets. As far as phi is concerned, phi does not have any point, so it is trivially open. We just need to write in sentences in statement format. Let XD be a metric space, phi be an empty set. We need to prove phi is an open set. So for this we need to prove phi is neighborhood of each of its points. But actually phi does not contain any point. So it is assumed that phi, if it would have points, it would become neighborhood, and since it does not have points, so it is considered to be neighborhood of each of its points. This one is by trivial, so phi is open set. Next, for the metric space X, we need to prove this is open set. To prove X is an open set, we are considering a specific element. This element is arbitrarily chosen. Let X be any element in XD, and we need to prove that capital X is neighborhood of element X, so that I can say it is neighborhood of each of its points and hence open. See, whenever we are dealing in metric space, there must be existing a metric under which I can draw a sphere containing element which is contained in X itself. Every sphere is contained in X, so that is why X is neighborhood of each of its points. Since here X was arbitrarily chosen, so if any point will be taken from X, capital X will be neighborhood of that point, hence X is open. In next theorem, in any metric space XD, every open sphere is an open set. Consider a metric space XD, open sphere in it. This open sphere, we need to prove this is open. Suppose this is an open sphere centered at A with some radius r, and if I need to prove this open, I will take element in this and I will show that sphere centered at that particular element is contained in this open sphere which is centered at A. So I need to show SXR1 is subset of SAR. X is arbitrarily chosen inside the sphere SRA. Let SRA be an open sphere in metric space X, and let small x be any element inside the sphere. I need to prove that sphere centered at X with some radius will be contained in sphere centered at A with radius r. So for this, since dxa is less than r, because x and A is the center, x is inside the sphere, so obviously the distance will be less than radius, and r minus dxa will be positive. So this is one of the positive term. We are considering this as r1. We will be taking this as the radius for the sphere which is centered at X. So basically I need to show that sphere centered at X with radius r1 is contained in sphere centered at A with radius r. So if we need to prove one set is subset of another, we need to take one element from the first set and we need to show the element belongs to the other set. By this we can show that one set is subset of other. So let y be any element of SXR1, then dxy will be less than r1 by metric definition. Also in metric triangle inequality I can say dy is less than equal to dax plus dxy, and dxy will be replaceable with r1 using 1, and dax plus r1 by the definition of r1 chosen can be equal to r. So now I have proved DAY, the metric from the center A with Y is less than R. That means Y belongs to the sphere itself. SAR. So I have taken Y as an element of SXR1 and now it is coming as element of SAR. So SXR1 is a subset of SAR1. SAR. By this we say hence every open sphere is open set. In next theorem, let XD be a metric space, then a subset G of X is open if and only if it is union of open spheres. If and only if states the result is true both ways. This is a metric and G is an open set inside metric and it is consisting of union of open spheres. If it is open, it is consisting of union of open sphere, and if it is consisting of union of open sphere, then it is open. The result we need to prove both ways. So for the first part, we are assuming G as open set. Let XD be a metric space and G as an open set of X. If G is empty, then there is nothing to prove because then it will be considered as empty class of open spheres. Union of empty class of open spheres. So let us assume G is non-empty. It must have some elements. Let X belongs to G, and since G we have assumed as open set, so it is neighborhood of each of its points. So it is neighborhood of X. X belongs to an open sphere subset of G. This is true for every element of G. So taking union both sides, belong will convert into subset because now we are in sets. Union of open spheres subset of G. So union of X is G itself because we have taken all the elements of G. So by this two-way inequality, G is union of open spheres. This proves the first part. Very simple, by the definition of open set only. Now for the converse part, I am using this margins so that we can remain on the same page. Conversely, let us assume G is union of open spheres. G is union of open spheres and we need to prove G is an open set. So if this union is empty, then since phi is an open set, so G is also open set, which will be proved trivially. So let us assume G is non-empty. The union is containing few elements. Let X be any element belonging to this union. If it is going in the union, it must be going in some spheres. G is union of open spheres, then X must be belonging in some spheres. Suppose it belongs to a sphere centered at A with some radius R. I need to prove this X is contained in some another sphere which is also contained in G, so that I can say G is neighborhood of X and so that I can say G is open. So since every open sphere is an open set, in the previous theorem we have proved. So now X, since it is belonging to an open sphere, so I must be getting an open sphere centered at X, which is subset of this open sphere centered at A. And this is by definition as open sphere is open. So by this actually I am getting the sphere is contained in G, and this makes G as open.